Do you have the pointer? Sylvia, do you have the pointer? Okay, so we have Riccardo Argurio who will tell us about non-compact TQFTs and non-invertible symmetries.
Okay, so let me start by thanking, of course, the organizers for inviting me to this very nice workshop. So today I'm going to talk about non-compact topological quantum field theories and their relation to non-invertible symmetries. So by non-compact, essentially I mean topological field theories with an infinite number of objects. I'll try to motivate why I want to care about them. So this is based on a paper that came out in the spring and two work in progress with all my nice collaborators here. Some of them are in the room. Okay, so let me first go very quickly about this first slide where, okay, I don't think by now I need to motivate the interest of topological field theories, but in particular, so since we started, the community started realizing that the topological defects are related to symmetries, and symmetries are obviously important for understanding quantum field theories, then let's say that the topological sector of quantum field theory, so the set of its topological defects, has become a very important thing to study. So, of course, so now focusing really on topological quantum field theories, then of course, I mean, topological quantum field theories are quantum field theories, so they can be studied. But besides that, they can be used they can naturally address topological defects, maintaining its, their topological nature. And also, as we saw in many of the talks, including many today, they play the role of the symmetry TFT, so they encode precisely the topological sector of a QFT. So let me also review very quickly what I will call now compact topological quantum field theories. Now I'm not sure it's exactly the same precise mathematical terminology that was used this morning, but let me, okay, so here I'm a physicist by background, so I'm not going to delve into the classification, but just examples. So let me just consider those that have been used in many physical models, which are the so topological quantum field theories with finite global symmetries, so which will be Zn or Zn times Zn, and these are the very simple examples. So Chern-Simons, abelian Chern-Simons in 3D, or BF theories in general dimension. And what I want to emphasize is that these theories can be formulated in a Lagrangian or path integral point of view, considering path integrating over connections which are in U1, so in a compact gauge group. And the order of the global symmetry is fixed by this, this level here, which has to be an integer, and it's, well, I call it n. And another perspective is to say that both of these theories have a finite set of extended operators, so lines in 3D, which so are simple Wilson lines, but which are topological, since the whole theory is topological, and they have this condition that tells you that there is a finite number. And so here I'm going to go very quickly here because I'm going to expand on both examples later. But so let me emphasize two of the uses that have been done of this compact TQFTs, which is in one case is so the idea of addressing topological defects with topological theories. So this has been used in massless QED, where the axial symmetry is famously ABJ anomalous. So at first sight, it might be one, like in all textbooks is written, it is broken at the quantum level, but as was emphasized in these papers 2 years ago, one can actually show that the defects corresponding to rational angles can be constructed using this kind of topological quantum field theories with symmetry Zn, where Zn is the denominator of the rational angle. So this is essentially the same idea of the fractional quantum Hall effect, but applied to these defects. And then this gives rise to non-invertible defects, because now when you fuse two defects, then essentially the fusion of the two topological quantum field theories will not be trivial when you take one angle and the opposite angle. And so this is related to the higher gauging of this Zn subgroup of the axial symmetry. There is a very similar story, well, not exactly similar, but from my point of view, very similar, which is a story which is, if you take the compact boson at rational radius, then here also you can play with a Zn subgroup of, let's say, in the simplest example of the U1 winding symmetry or the momentum symmetry, and use this gauging to establish T-duality as a symmetry of the theory. Essentially, if R square is n, then you gauge, and then you do a T-duality and you go back to the same radius, so this becomes a symmetry. But because the symmetry involves a gauging, then again it's a non-invertible symmetry. And again, okay, so itself, here in this case, this symmetry can be nicely encoded in the symmetry TFT, which again is going to be a compact TQFT, in this case a BF theory. Okay, so that said, in both of these examples that I just explained, the symmetry content of the theory is actually involves some U1s. Like the axial symmetry at the beginning is a U1, and also the compact boson has a U1 times U1 symmetry. So, okay, so then maybe it would be interesting to have a description which TQFT which handles this infinite number of elements. Okay, so in other words, the idea would be to have a TQFT which has a U1 or a continuous symmetry as the global symmetry. Okay, so this I understand that it's something that is not easy to define mathematically, but let's, as physicists, let's take the examples of before and twist them. So let's consider just Chern-Simons or BF. And the idea is to consider, instead of U1 gauge groups, so we just consider exactly the same thing, so path integral over connections. But now the gauge group is going to be R. So let's see what changes. And so this is, of course, has been introduced early this year by these papers. Many of the authors are here. So, okay, so let me review very quickly. Andrea also discussed briefly these things, but let me go over again. So, for instance, so there are two options. So let's focus on BF theories in 3D to be very simple. So we have only lines. And so the first option in the BF theory, we have two connections. So let's take only one in R and the other in U1. So when I say that one connection is in U1, then it means that it has quantized fluxes. But if it's in R, then the fluxes have to be zero. Then if you perform the path integral, let's say, then you realize that the objects in these theories are lines which take values in U1 and the others in Z. Okay? And so you see that we have an infinite number of lines. And these, they as in the usual BF, they generate a symmetry. In this case, it's a U1 times Z. Also notice that I don't need to specify a level here, because since one of the fields is in R, I can rescale it for free. There is no problem of quantization of fluxes, and so I can set it to 1. It's arbitrary. The other option is to have both fields in R, and then in this case both have zero flux. In this case it's simpler, so we have all the lines actually have take values in R. So in other words, I'm saying they are labeled in R. And so the global symmetry is R times R. So in both of these examples, the number of lines is infinite. This is, in some sense, expected, since we are aiming, since these theories have continuous symmetries. So let's see first use of this kind of non-compact TQFTs. So let me again, so now in more detail, talk about massless QED. So massless QED has an ABJ anomaly. This equation featured several times this week until now. And then, okay, so obviously, so it means that the current, axial current is not conserved, but I can try to make a topological defect by bringing the right-hand side to the left-hand side, so I can write this topological defect. But famously, this is, so now A, of course, is the gauge field of QED, which is compact. So this Chern-Simons term is invariant under large gauge transformations only if, well, the overall coefficient is integer, the Chern-Simons level integer, which means that alpha has to be 2 pi rotation, so trivial. Okay. So what we proposed, so this was the starting point of the previous discussion about the rational angles, but what we propose is that, well, there is a way, so instead of using the fractional quantum Hall effect trick, here we propose to couple the U1 gauge field to this non-compact TQFT, actually. So you see, this is, so C is in R, phi, capital phi is in U1. So this is a kind of a mixed BF theory, but then we have also like a Chern-Simons-like term here. So the coefficient here is meaningful because I use the rescaling once to set this coefficient to 1, then this is meaningful. And then you can easily see that naively integrating out C and phi, you get exactly the term I wanted here. But on the other hand, you can show that this, you can see that this topological field theory is perfectly well defined. It's gauging. Okay? And so what we say is that this is well defined for any value of alpha. And so here I think I put this citation too early. What I meant is that then I can dress the topological defects by this topological field theory and define these defects for any alpha. Okay? So now I can cite Nameki and friends, where there was a similar proposal achieving the same thing, but a different proposal. We can elaborate on the difference fast. So these defects are also non-invertible. So if you fuse this defect with the one with the opposite angle, d alpha times d minus alpha, work out a bit, we will find that this is proportional to the, essentially to the defect where I set alpha to 0, but this is not the identity. It's actually what you would call a condensation defect. It is a condensation defect where actually all the magnetic one-form symmetry, which is there in QED, so the magnetic one-form symmetry is condensed on the defect, condensed with so it's gauged but with flat connections. Okay. And okay, so another thing one can ask is what is the relation between these defects, this proposal, and the one which was found before for the rational angles. So essentially, the idea is what happens if I tune this alpha to have a rational value, and then we can compare the two defects, and the comparison is this. So the defects we propose are proportional, are actually the fusion of the defects which implement this rational, the ones which were proposed in this paper for the rational angles times the condensation defect. So in other words, it means that the defects which are valid for any angle when reduced to the rational angles are in some sense a non-minimal non-minimal in the sense that they also are fused with these condensation defects. But okay, so might say that it might be a slightly unsatisfactory feature, but let's see how they act on top lines. So as you know, if you know how it works for the rational angles, the non-invertibility of these axial symmetry defects manifests itself when when Toft lines are passed through the defects, or vice versa. In other words, so the Toft line gets attached to a surface here, and so this is exactly the same here, and essentially it's a generalization to any angle of what happens for the rational angles. But what happens, what is interesting is that this is the junction. So in other words, how this surface attaches to the defect is by this junction. So this phi, capital Phi, was the U1 field on the defect, on the TQFT that addresses the defect. So you see that we have this junction, and the interesting thing is that this junction does not depend on the angle. Okay? So in other words, the action and the junction is universal, which was not the case in the case of the rational angles. So in other words, also when you pass through also the condensation defect, so D0 is the condensation defect, you see that there is no surface attached, but there is a junction, which is attached, and this is why it is a condensation defect. Okay. So let me maybe go a bit more quickly. So we can also we can look at the same theory from the perspective of the symmetry TFT. So this is exactly the same symmetry TFT that was displayed in the talk by Andrea. Indeed, we extracted it from here. So this is about, this term tells us about the Toft anomaly of the ion axial, which is not going to play any role. And this term here is the one which encodes the ABJ anomaly. And so the symmetry TFT, as was already stressed by Andrea, it is also a non-compact TQFT because it has to have this U1 times U1 symmetry. Very good, and then we can go proceed and look at the operator content of this symmetry TFT, and we realize that because of this term, some operators are non-genuine. So in other words, these operators here have like a higher dimensional surface attached to them. But as we saw, so here there is a very similar trick that these operators can be made actually genuine. So we can remove this attached surface by exactly the same kind of trick that we used for on the boundary. So it means that we can dress these operators, which are the ones when pushed to the boundary become the axial symmetry defects. We can dress them obviously by the same TQFT, and then there is a similar story that we can do on these other operators. So in other words, in this theory, we are using non-compact TQFT twice because the symmetry TFT is a non-compact TQFT, and then to make the operators it has genuine, we use another non-compact TQFT. Okay, so this is some thing that we are finishing now, which is to generalize the symmetry TFT to a situation where we have, so this is an example which is more general than QED. So it's allowing also for the presence of this other mixed anomaly, which is actually something which leads to the presence of a two-group. So the idea is to have a situation where we have both a two-group and an ABJ anomaly. So ABJ anomaly means non-invertible defects in this case. And then it turns out, so this is something maybe fun fact, that now the defects, the axial defects, are going to have both a topological, non-compact topological theory dressing them and a surface attached, because it turns out that for the two group, it's better to have an attached surface. Okay, so let me now go on a different example and a different use of non-compact TQFTs, which is again another example which is like a paradigmatic example. Let's take a one compact scalar in 2D, and so this is the action, so it's compact, and R square is the radius, and it's very well established that the symmetry, the zero, these are all zero form symmetries. There is a momentum symmetry and a winding symmetry. And this is the usual symmetry that there is for any R. So again, the symmetry TFT, so is a 3D BF theory, and it has to be of a non-compact type, and the most economical way to write it is this one. Again, the level is set to 1, and the lines are, as I said already before, so these are the two kinds of line labeled in R. Now, so this symmetry TFT seems to have a symmetry which is R times R. How do we go to U1 times U1? Well, as now I put a picture, and now you recall everything you already heard this week about symmetry TFT. So we have some boundary conditions that at the topological boundary and some physical boundary conditions here. And so the way we choose to set this boundary condition is this way. So on the physical boundary, we put this conformal boundary conditions. So these are morally the same that appeared in Iñaki's talk earlier. And okay, and then at the topological boundary, we impose boundary conditions, which essentially impose. So the idea is to select select a set of lines in the bulk that braid trivially. And so one way to do that is this. And so this set of lines is parameterized by a parameter, which turns out to be the radius. Okay? So what is very interesting from this perspective is that the radius is encoded in the boundary conditions, okay? In the topological boundary conditions. And so then changing the boundary conditions is notoriously a topological manipulation in the QFT that is supposed to be represented by this setup. And so it means that rescalings of the radius should be seen as a topological manipulation in the CFT. So let's see how to do that. Well, okay, so I want to rescale from R to R prime. Then the first thing to do is to gauge the winding symmetry. Again, the idea of gauging here is preserving the flatness of the connection, so I don't introduce any degree of freedom by doing this gauging. So this essentially removes all the winding modes, and so essentially decompactifies the boson. And you see that by consistency, we have to add all the continuous momentum. So now we end up in a theory which has momentum R as momentum symmetry. And then we just gauge a Z in this R, which will be specified by a periodicity which I can choose to be R prime. Okay, so these are the two. So you see that I have two gaugings to go from R to R prime. And then obviously the new radius R prime can be chosen to be 1 over R, so that I can compose this rescaling with the T-duality and then provide the symmetry for the compact scalar at any R. And this is obviously a non-invertible symmetry because some gaugings are involved. And okay, so let me end. So the symmetry TFT, so you might say, how is this duality, non-invertible duality encoded in the symmetry TFT? Because the symmetry TFT was only for U1 times U1. Well, this is a trick that was already explained 2 years ago. Then this, the duality symmetry actually arises, the way it's constructed is by a condensation defect in the symmetry TFT, where we gauge an R, the diagonal R in R times R, and this opening these defects can be shown to lead to the non-invertible lines at the boundary. Okay, so I have 0 minutes to tell you the outlook. So I tried to, let me just say the punchline. So, okay, so I tried to convince you that non-compact TQFTs, how to use them to do several things. What I want to emphasize is that non-compact TQFT, so I mean, continuous symmetries are abundant in QFTs of interest. So then these theories will have infinite collections of topological defects. So I think it's upon us to have a closer look here. I swept under the rug all the difficulties in dealing with non-compact TQFTs, but there are, of course, all the proportional two signs that you saw is because the coefficient is infinite. So, okay, so the message here is really to say, okay, I think we need to use these objects, and so I'd be happy to discuss with any of you about this non-compact TQFTs if you have ideas how to have a rigorous definition. Thank you.
Any other questions?
Hi. So you should also study Tambari-Yamagami symmetries for the non-compact boson then. It's
Do you have ideas? Or
No, you can do it. It's something that exists.
Okay.
Can I make a comment?
We can.
I mean, the honest, undisclosed statement is that the mathematicians here, Enriquez and his students, they're working out the TY for R.
That's very interesting. I'll be thrilled to know more about that.
Typeset for the name.
Okay.
Any more questions? If not, let's thank Riccardo again.